So that's the only problem, probably the only inorganic chemistry topic that you have to study in A2. That's a transition metals. Now the first thing is, how do you define a transition metal? So the technical definition is that it's something that has it's an element which could do a few things. An element that forms or which forms stable ions, forms stable ions with incomplete d subshells. So with incomplete d subshells. That is the technical definition. Okay, it's going to have stable ions, and those stable ions are going to have incomplete d subshells. For example, iron is a transition metal because iron has 26 electrons. So the electronic configuration for 26 is going to be 1s2, and it's going to be 2s2. Then it's going to be 2p6. As a pair, there is going to be 3s2. Then there's going to be 3p6. Then you have 4s2. That's 20 electrons. And then the remaining 6 electrons, they go into the last subshell to be filled according to the Aufbau principle is going to be the D. There'll be 6 electrons going into the D subshell. I'm just writing it in the correct sequence. That's why. So it's going to be 4s2 and then 3d6. So this is what iron is. But remember that the definition of transition metal is not about the atom. It's about the ion. What ions does it form? It forms it has several oxidation states. The common ones are, so now the common ones are 2+ and 3+. So I've got 2 irons. If it's 2+, so if it's 2+, remember the electrons are always lost from the outermost shell. That means 4s is gone. That's 2+. And if it's as if the same thing is 3+, it could be 3+ as well. So if it is 3+, then electrons are lost from the 4s, and they would also be lost from the d subshell as well. And there'll be 5 electrons that are going to be left in the d subshell. So it's going to be 3d5. But anyways, in both cases, the ions are stable. These 2 ions are really stable. I mean, you have a lot of iron salts that have these 2 ions. And in both cases, the important thing is in both situations, okay. So in both situations, the important thing is, let me highlight this. So now in both cases, the important thing is that the D. So the important thing is that the D is incompletely filled. That's what's important. Is that clear? But a definition, I haven't explained what the definition is, but do you understand what the definition is? Is that clear?
Yes, sir.
So any element that has ions, stable ions, and those stable ions have incomplete d subshells, that's what a transition metal technically is. Why that is, that's a different story, but that's what the definition is, stable ions. So based on this, some of the ions that you think are transition metals, so where do you actually find transition metals in the first place? Like if I open the periodic table.
Sir? Sir, 10 होगा?
10 तो वैसी transition metal नहीं है. I'll explain just one second. So this is your periodic table, right? So let me just take a snapshot. So what you think are transition metals, they're not actually not all of them are actually transition metals. If I paste it over here, so the very first thing is you believe that this thing is transition metals, right? Okay, the middle part, all of this. These are somehow your transition metals. Okay, these ones over here, right in the middle, right? Now remember one thing, okay, these are not really transition metals. Sorry. I said, now remember one thing. I said, remember this thing. Okay, these are not really transition metals. These are known as D block elements. A lot of them are actually transition metals. So the technical word for all of these is that they are D block elements. So why are they referred to as D block elements is that when you're filling electrons into these elements, the last electron goes into a D subshell. So that's why you call them last electron, according to the off-bow principle, goes into a D subshell.
Sir? Sir, F block elements होते हैं?
होते हैं, हमने उसका कुछ भी नहीं करना. वो F block वो नीचे होते हैं, जो बिल्कुल बॉटम पे नहीं होते. ठीक है. वो जो दो एक्स्ट्रा नहीं यहाँ पे शुरू हुए हैं, these are F block, lanthanides and actinoids. Forget it, they're very rare, they're very unstable. Actually, I mean, if you look at the periodic table, the whole periodic table, ये जो bottom पे जो दो है ना, it's these ones. I mean, this 57 to 71 is supposed to fit over here, ये पूरी row, and 89 to 103, that's going to fit over here. But just ignore them, okay? There's no, I mean, they don't have a lot of importance. They're very unstable and they're very rare as well. Uranium is one of them, okay? So anyways, D block elements. As I remember, the important point, these are not transition metals. These are D block elements. A lot of them in this D block are transition metals. Okay, so most D block elements they have stable ions with incomplete D subshells. With incomplete D subshells. But at the same time, most of them will have D block. Most D block elements have stable ions that have incomplete D subshells, but not all are transition metals. Remember that as well. For example, zinc is not a transition metal, although it is in the same block. It's a D block element, but it's not a transition metal. A transition metal has to fit this definition. So zinc, similarly scandium, and some other as well. We're only interested in zinc and scandium. I mean, the first row of the transition metals, these are the common ones. The bottom one, these are not very common, so you don't really talk about them. The top row, that's the one. Those are your everyday metals. Those are the ones that you see every time: iron, cobalt, nickel, copper, etc. These are the common ones. but most of these down here, you've never actually heard about them. TK, TCMO, the molybdenum, you've probably never heard about them. But a yttrium, no one has ever heard about it. TK. So we're only interested in the first row, basically. So remember this zinc, scandium in the first row are not transition metals. And there's a reason for that, and the reason is that they don't have incomplete d subshells when they form ions. So if I write down the electronic configuration of zinc, the electronic configuration of zinc is, so the electronic configuration of zinc is 30 electrons. So it's 1s2 and 2s2 and 2p6 and 3s2 and 3p6, and then you have 4s2, and then the last 10 electrons go into the D. So the zinc ion, the stable ion of zinc is zinc plus 2. That is the zinc ion. Now the zinc ion, the electronic configuration is the outer electrons will be lost. So its D subshell is going to be completely full, which is why it is not a transition metal. It does not fit the definition. So it's a full D subshell. Hence, it's not transition. Technically, according to the definition, this is not a transition metal. Similarly, you have another one, which is scandium in the first row. That's also not transition, because scandium has 21 electrons. 21 electrons, the electronic configuration is going to be almost the same. It's going to be 1s2. Then it's going to be 2s2, 2p6. That's a 3s2, 3p6. 4s2, that's 20 electrons, and 21 would be 3d1. Now the stable ion of scandium is +3. So if it's +3, that means electrons are lost from the outermost shell. And so these electrons are gone. So it doesn't even have a D subshell. So definitely not a transition. Definitely not a transition metal. So that's also not a transition metal. So remember, for a transition metal, you've got to have incomplete D subshell when you form an ion. Otherwise, you're not a transition metal. Copper is sometimes not behaving as a transition metal as well. For example, copper 2+ will have transition metal properties. Copper 1+ will not have transition metal properties. So copper 2+, let's just copy the electronic configuration. ये वाली copy कर लेते हैं. And also for copper 2+ and copper 1+. Now copper had 29 electrons. So for 29 electrons, the electronic configuration, remember copper was this special case where the electronic configuration, the D got completely full, and then the 4s had 1 electron. And here's another one where you have, both of them are going to have the same electronic configuration, but one of them is going to lose copper 2+, that's going to lose 2 electrons. So kya hoga? The 4s will be lost. And now instead of 10 electrons, you're going to have 9 electrons. So it is a transition metal. But copper 1+ is not going to behave as a transition metal, because if it's 1+, then the electrons are lost. So copper 1+ will not exhibit transition metal properties. So no transition metal properties for copper 1+. while copper 2 plus, it is a transition metal because its ion has incomplete d subshells. So ये तो खाली definition थी क्या? I told you what the definition is. Just remember that not all of them are transition metals. Even copper is sometimes doubtful. Sometimes it behaves as a transition metal. Sometimes it doesn't behave as a transition metal. Scandium and zinc are definitely not transition metals. The rest are iron, cobalt, nickel, manganese, chromium, etc., vanadium, titanium. They're kind of transition metals. But even in their cases, you have to look out for if the ion has incomplete d subshells or not. If you look at vanadium has several oxidation states. Like if vanadium is +4 or something, then it's definitely not going to be a transition metal. But you would have to watch out for when they're forming an ion, is the D incomplete or not? If it is incomplete, then it's a transition metal. If it's not incomplete, then it's not a transition metal. So is this point clear? You want to clear this point?
Yes, sir.
Bakiyon clear, Alicia, Anna, is this clear? Abia, what's the question? Oh, sorry. Chalo. अच्छा ये तो खाली वो है कि but the question is like I keep saying कि so I keep saying that it behaves as a transition metal, it doesn't behave as a transition metal. So the question now is, as I said, there's a small thing I want to cover up, which you've already studied in AS, and that is that chromium and copper have this special electronic configuration. Usko hum side pe likh lete hain. Okay, I mean, they're obviously going to ask you, first thing about the question is that they're going to ask you about the electronic configuration. So just remember that there are two special cases. I'll just write this down either side pe. Top pe likh lete hain. Just remember that there are two special cases, and you have to know the electronic configurations. Okay, AS there were exceptions. One was copper, the other one was chromium. इसी को सही कर लेते हैं. अच्छा, so copper, forget 2 plus. So copper had 3D10 4S1. Instead of, it should have been 4S2 3D9, but it wasn't. Or the other one was chromium. Now, in the case of chromium, you've got CR and it's 24. So the electronic configuration, instead of being 4S2, 4S pehle fill hota hai, theek hai? So instead of being 4S2 and 3D4, it was actually 3D5 and 4S1. Theek hai? So there were these two special cases whose electronic configurations were kind of slightly different than all the rest. So you had these two. As you had these two special cases. As coming back to the old point, which is what's a transition metal, what's not a transition metal. Technically, we've figured out which one is a transition metal, which one isn't. What happens if you are a transition metal? If you are a transition metal, you'll exhibit certain properties that are transition metal properties. And levels wala hai, there are a couple of properties which is why you call them transition metals. So you've got kya properties, and you've got and that's all O levels.
Act as catalyst and colored in.
So transition metal properties. Now iske baad se the whole chapter is about discussing these properties, like why do they even have those properties to begin with. So they have like 5 properties, 5 main properties. Number one, they've got higher density. That's So that's the first one. Second one is that they have high melting and boiling points. So high melting and third one is that you got what's the third one? Third one is that they have variable oxidation states. And fourth one is that they are colored compounds. They have colored compounds and इसके word use करो complexes. ठीक है, we'll learn what a complex is. And fifth one is okay, they're good catalysts. So in total, you've got these 5 properties, and we have to basically just justify all these 5 properties. Okay, that's what the whole chapter is about. इसके अंदर खास तौर पे this colored complexes, that's the one that we're going to go into a lot of detail. ठीक है, नहीं वो तो see metals है ना, so obviously they're going to conduct. Like, see what's so special about transition metals. ठीक है, so I mean these are properties compared to other metals. Like, what's so different about? Actually, this is something that we're going to go into a lot more detail. That's colored complexes. So starting with the pehli teen hai na, we can just do them very, very quickly. Like, why do they have high density? Why do they have high melting and boiling points? Why do they have variable oxidation states as well? So the first 3. Okay, let's start talking about the first 3. Actually, if you're not a transition metal, these properties, you can have some of them, but you're not going to have all of them. Okay, for example, zinc के जो compounds है ना, they're colored. They're not colored. Okay, that's one. So zinc is not a transition metal. It doesn't really have a high melting point as well, and it also doesn't. What it doesn't do is एक और चीज थी कि it doesn't have variable oxidation states as well. But the number one thing that a transition metal is identified by is its colored complexes. A lot of things have high density, a lot of things have high melting and boiling points as well. A lot of things have variable oxidation states as well. I mean, chlorine has variable oxidation states, sulfur has variable oxidation states. So even that is not very unique. Catalysts and colored complexes, that's kind of very unique for them. As starting with the first thing, and I'm going to compare ये जो पहले 3 है, high melting points, high boiling points, variable oxidation states, and high density. I'm going to compare them with calcium because calcium is right next door. Calcium के बाद ना एकदम से कुछ होता है and they become transition metals, right? I mean, scandium is not a transition metal, but after that, transition metals they start. So what happens after calcium that they actually become transition metals and they've got high melting and boiling points? So if I look at also the high density, high melting and boiling points, right? So discussing the first one. That's a high melting points, melting or boiling points. And also high density. All of this could be covered in the same thing. And the comparison I'm doing it with is calcium. Okay, so compared to a normal group 2 metal like calcium. Okay, so comparison bhi dekh lo, okay, if you talk about calcium melting point, that's 842, right? And if you compare it with let's say कोई भी कर लेते हैं, iron कर लेते हैं, the iron melting point, that's almost double. ठीक है, Same with density. Like if I compare the density of calcium, the density is not going to be that high. It's going to be 1.55. It's greater than water. It's going to sink. Like if I compare it with iron, the density is like 8 times more. I mean, that's a lot. There's a huge difference. That's 8 times heavier than calcium. So what's the reason for that? The reason is it's this structure they're all metallic, right? So they all have a giant metallic lattice. And what's really a giant metallic lattice? It's a lattice of positive metal ions, and they are surrounded by delocalized electrons. So here's what it's going to look like. There's a here's how it's going to look like. There's positive metal ions, and there'd be lots of positive. So there's going to be lots of positive metal ions in the lattice. So you've got, और इनको arrange कर लो properly, ठीक है? So that's one. I said they would have a very regular arrangement with almost no gaps between them. So because it's a solid metal, they'll be kind of tightly packed. So that's and we can double this. So that's what a metallic lattice looks like. And let's say this is calcium, right? So if this is calcium will have what charge? Every ion will have a charge of +2. So all of them will have a charge of +2. I'll just copy this. So all of them will have a charge of +2, and all of them will lose 2 electrons each from the outer shell. And it's going to be surrounded by electrons, lots and lots of electrons that will be moving around, delocalized. And these electrons will be part of the delocalized electron cloud. So what is happening is, what is metallic bonding? That you've got regular positive metal, a lattice of regular positive metal ions. So you got regular arrangement of positive metal ions. और साथ बीच में ना you've got these delocalized electrons. And what is happening is that between them they've got this attractive force. Okay, they're attracting each other. So the positive metal ions and the delocalized electrons, they're kind of attracting each other. So there's this attractive force. Positive ions, they get attracted to negative electrons. That's what a metallic lattice looks like. And that's your typical calcium lattice. उसी तरह होगा. Is this clear? ये चीज clear है?
Yes, sir.
Yes, sir.
So आगे move कर जाओ. So how is a transition metal going to be different? The reason it's going to be different is that one thing is that it will be smaller in size. Okay, so the lattice will be exactly the same. Okay, एक जो difference है ना, उसका जो lattice है, मैं पहले वो difference पहले note करा दूं. One difference is that the charge is going to be higher, and there's going to be a the charge is going to be greater. So let's say वो सारे के सारे ना, let's assume that they are +3, right? And I'll explain why the charge is going to be higher. So the ions will have greater charge, and if they have greater positive charge, there's going to be a lot more delocalized electrons as well. So they're going to have, there's going to be a lot more delocalized electrons. So I'm going to draw more electrons. So it's a metallic lattice which has more positively charged ions, a higher positively charged ion, and with a lot more delocalized electrons. So उनके बीच में the attraction will be very high. There's going to be very strong attraction. Plus, there's another thing, and that is that the size of the ion will be kind of smaller as well. So they'll be more tightly packed as well. So आपका जो lattice होगा ना, that's going to be, comparatively speaking, it's going to be more, I mean, the electrons are going to be, they'll be higher in number. Plus, they'll be more tightly packed as well, and they'll be smaller in size as well. So, दोनों को comparison करोगे ना, calcium would look like this. The transition metal would kind of look exactly the same, except that it's going to be, the ions will be smaller in size. The one thing that will happen, and let's call this iron. Okay, this is what iron's lattice would look like. उसकी मैं reasons बताता हूँ why would it? हाँ.
सर क्या ट्रांजिशन मेटल्स के अंदर ज्यादा इलेक्ट्रॉन्स होते हैं delocalized as compared to metals?
नहीं, वो तो मैंने बता दिया, अभी मैंने reason नहीं बताई why is the, अभी तो खाली ये बता रहा हूँ कि why is it going to be stronger, right? अच्छा, तो पहले तो मैं overall difference बता रहा हूँ. This is going to be the overall difference, and we'll discuss the reasons why this is the case. नहीं, Alicia, उसके ऊपर भी आता है, even if you compare with CO2 plus, I'll explain that. अच्छा, अभी तो overall बिल्कुल general broad reason. ठीक है, this is the overall difference between a transition metal and a calcium metal. Calcium lattice, it's going to be a bigger ion, it's going to have lesser charge, less delocalized electrons. Transition metal, it's going to be a smaller ion, the ion will have a greater charge, and there's going to be a lot more delocalized electrons, and the lattice will be more tightly packed because the ions are obviously smaller. The attraction क्या हो जाएगी? Automatically ज़्यादा हो जाएगी, because if you have a higher positive charge, okay, so what if you have you've got a higher positive charge, so your ion has a higher positive charge, plus at the same time you've got more delocalized electrons. Then definitely there's going to be more attraction, right? So you got a higher positive charge, they're closer together, and there's more delocalized electrons. So wo jo attraction hogi na between the electrons and the positive ions, remember the electrons are acting as a glue in the metallic lattice. What happens is that the electrons are like acting as a glue, just a glue lagti hai na. You got a positive ions, and in between the like electrons that are stuck over there, which are negatively charged, and then you've got another positive ion, so they're all attracting each other. So the positive ion attracts electrons, electrons attract positive ions, positive ions, they attract electrons. ठीक है, so there's a mutual attraction that's happening between positive ions and electrons. तो जितने ज्यादा electrons होंगे और जितना ज्यादा positive charge होगा, the greater will be the attraction, right? So that's number one. That's the reason why transition metals have a stronger metallic lattice. And now what we're going to discuss is, why do they have more delocalized electrons? Why do they have a greater positive charge? A smaller ions bhi hain. Ye bhi maine sorry nahi likha. They've got a higher positive charge plus smaller ions as well. So they've got a smaller ionic radius. So that kind of translates to higher charge density. Okay, so that translates to higher charge density. The ions have higher charge density. So like a general statement to clear है कि what is a strong metallic lattice? Is that clear? Very clear. Let's
Yes,
see.
sir.
Sean, is this clear? अच्छा अब ये कि now the question is why, okay? Like why do transition metals have, and you can even check the ionic radius of data booklet, just a second. Equally with the second. That's your data booklet, right? Now obviously you don't have a data booklet anymore. Your values printed only uske saath with the question. So now somewhere over here there's they actually have ionic radiuses. So if you compare it with calcium, calcium is in period 4 as a group 2, sorry. Calcium is 0.197, right? The calcium ion is 0.099. Or calcium will compare 0.099, right? Look at transition metals and their ions. All of them are smaller in size. Calcium, remember, was 0.099. These are like almost half the size. 0.099, 0.055 iron 3+. Even iron 2+ is small. Mn 2+, Mn 3+, TK, they've got variable oxidation states. Vanadium 2+, vanadium 3+, they all kind of have really small ions. So पहला जो question है, पहला जो why do they have greater charge and why do they have smaller size? Because the first thing is, when you move across the period, when you move across the period, what happens is that they all have the same kind of electronic configuration. Like if I have calcium, so I will explain kar raha hu, if I have got calcium, that's 20 electrons, right? And I've got scandium, and then I've got scandium ke baad vanadium, titanium. Just one second. Scandium, titanium, vanadium. As a scandium, then I've got titanium, then I've got vanadium, then I've got chromium, then I've got manganese. So this is 21, this is 22, this is 23, this is 24, and this one is 25, and so on. Which are transition metals. So what is happening is that the electronic configuration of calcium was, they all have kind of the same electronic configuration, at least the atom. What is that electronic configuration? It's you got 3 shells. All of them have 3 shells when they form an ion. Okay, and we're talking about the ion. The least a transition metal forms is +2. I mean, all of them kind of forms, they all kind of form +2 ions. Okay, why do they all form +2? Because agar yahan pe electronic configuration dekho na, to like all of them kind of had 2 electrons in their outer shell. I mean, all of them. So the outer shell was lost. That was always the one that was lost at the start. Okay, so they all kind of have +2 oxidation states. अच्छा लेकिन हाँ
सर आयरन 3+ जो है वो इसके क्या?
नहीं वो इससे आगे चलता जा रहा है ना. अभी खैर मैं एक छोटा सा पॉइंट कर लेता हूँ, टाइम खत्म हो गया. That point is that when you move across the period, right, they all have the same shells. Even when they form an ion, it's just 3 shells, right? All ions, when they form an ion, have the same number of shells. Same number of shells. The outer shell is lost. So they pretty much have 3 shells. Was your 4s thana, that is lost. Calcium also has 4s. So when they form ions, they have the same number of shells. But what is happening is that the protons are increasing. So the number of protons increases. So that leads to more attraction. So more attraction for valence electrons. And that is why when you move across the period, the ionic radius decreases. And the ions, they continuously become smaller and smaller. The ionic radius, it eventually decreases. Okay, is that clear? General trends across the period. Whenever you move across the period, even so transition metals, when you're moving across the period, you got more protons. Okay, manganese has 25 protons. It has the same number of shells as calcium. Okay, uske paas bhi 3 shells and uske paas bhi 3 shells. And this also had 4s2, this also had 4s2. The outer shell was lost when they turned into ions, but to piche kitne reh gaye, you got just 3 shells. So because the number of protons are continuously increasing, so the attraction for electrons or the valence electrons, it also continuously increases. So isliye across the period, generally what happens is the ions become smaller. तो ये एक डायग्राम बस मैं में दिखा देता हूँ. ये उसमें भी पढ़ा था कि AS में भी पढ़ा था कि it's I'll just copy this. Okay, this isn't something special about transition metals. It happens across the period. Okay, whenever you're going to move across the period. Okay, this thing will happen whether you're a transition metal or whether you're not a transition metal. Pehle period में भी ये issue है कि when you move across the period, the atom size becomes smaller, although the shells are the same. Like due to more attraction from the nucleus, the size of the atom continues to decrease. So calcium यहाँ पे बैठा हुआ है, and all of these transition metals, they become smaller and smaller as you move across the period. तो ये पहली बात clear है? For valence electrons, and the ionic radius decreases, ठीक है? अच्छा ये सारा clear है? ये भी हमने सिर्फ एक statement लिखी है कि which is that कि छोटे क्यों हो गए थे? Transition metals, right? Is that clear? अभी सिर्फ हमने वही discuss किया why what
Yes,
happened, what happened over here? Why did they become smaller? So you got more protons. So the size of the atom will shrink slightly because of more attraction. Okay. Sana, is this clear?
But,
Is this clear?
sir,
Anji.
calcium doesn't have the D subshell, so how is it smaller? Shouldn't it be larger?
Calcium is larger. No, calcium has, how many shells does calcium have? It has 3 shells, right?
Oh, okay.
वो तो subshells different. No? Subshells तो हैं कि भी वो S में या B में या D में, ठीक है? But it is the 3rd shell, right? And all the other ones, they also have 3 shells, right? The outer 4s is lost. ठीक है? So they all have 3 shells, but you got more protons, so that's why there's more attraction. So when you move to the right, it becomes smaller. ठीक है? Clear? तो ठीक है, बस हमने इसी पॉइंट पे खत्म किया कि अभी पहला पॉइंट के भाई ये छोटा क्यों था? हाँ जी.
सर आप इस लेक्चर के लिए सर रिकॉर्डेड लेक्चर जो ये वाला है सर आप इसकी लिंक सेंड कर सकते हैं क्योंकि जो बाकी हो क्योंकि सर वो जो बाकी था तो सर जमल्ड अप उसके अंदर एग्जैक्ट आइडिया नहीं है मुझे था.
नहीं वो इसमें जमल्ड अप नहीं है, वो इसमें ना ये देखो कि पता नहीं खुला होगा. ये मैंने लिंक भेजा इसका, तो इसमें ना ये जो लेटेस्ट है ना, ये डेट वाइज देख लो 9/26, ठीक है। आज पता नहीं क्या है, अच्छा आज 26 है ये। अब ये बल्कि आज की फोल्डर बना हुआ है, अभी इसमें वीडियो नहीं आई लेकिन ये आ जाएगी, ठीक है। क्लियर है?
ओके सर।
वो इस तरह डेट वाइज देख लो, 14/9 फिर 16 है। इसमें A2 जो लिखा हुआ है ना, ये आप लोगों का है, जो A2 कैम A2 वाला, ठीक है। वो अक्टूबर नवंबर रिवीजन वाला ना करना, ठीक है।
ओके सर, थैंक यू सर।
चलो ठीक है, ओके ओके एवरीवन, टेक केयर,
ओके सर।
हाफिज।